Good afternoon, everybody. My name is Megan Johnson. I'm the CARA Operations Lead, and I've also been leading the training for the CARA team for about 3 years. So the three presentations I'm going to give today are part of our advanced training that we've been developing. Gets into more of the theory in CA, and in previous MOWGs we've done some more broad training. So today I'm going to start by talking about probability of collision, how we calculate it, why it's important, all that good stuff. And in particular, we'll talk about the 2D PC, which is our main method to calculate PC. But we'll also briefly touch on the 3D PC method, positive definite covariances, and the Monte Carlo calculation, which is another way we can calculate PC. So what is probability of collision? It represents the likelihood that the range between two objects may become less than some radius r during the encounter time interval. So what is the likelihood that your missed distance is less than your hard body radius, which is our radius r that we define in CARA? And we use that as the sum of the hard body radii of both our primary and secondary object. And we'll talk about that more. So you could say it's the probability of hard body incursion. And so we need our missed distance, our event covariance, and our hard body radius in order to calculate the PC. And so we'll walk through how we come up with all that information. But first, here's just a picture of an event where you have a primary object and a secondary object. You've got this missed distance vector between the two. You know something about the velocity that the objects are traveling in. And you have arrow ellipsoid about the object. So this is the different information you need to calculate PC. Before we get into how we're actually going to calculate it from our diagram, let's talk about why PC is important. So it really is the single most important piece of data that we have when we evaluate a conjunction event and make a recommendation to a mission whether or not they should maneuver. And this is because it's considering the missed distance and the uncertainties of an event. And that directly contrasts with using the missed distance, which is just using a single piece of information. And so when we talk about, is this event risky, if we're just thinking about missed distance, it may not get us very far, because what is a small miss? How do we know what is small? You can have different PC values for a similar missed distance, whether it be high or low. And so that's where the PC comes in, where you take that missed distance information and use the other information you have about your event, like your uncertainties, to find this probability of collision. Even though it's very important, PC is not the embodiment of all risk. It is not the only thing that we're going to look at to make a decision, but it is very important. Evaluating OD is probably the other very important piece of information, but we look at a lot of data. And so just to get back to miss real quick, in CARA we have PC thresholds for different action that we're going to take, but we don't actually have a threshold for missed distance because, as I was saying, we really want to look at the PC and not just the miss. We do filter our screening data initially based on miss, but that's going to be 20 to 30 kilometer type filters just to get a manageable amount of data for us to process. All right, so hopefully we're convinced that we need to calculate PC. How do we do that? We have three main methods that we could use. The one I'll talk about the most is the 2D probability of collision calculation. It's the most common in industry. It's what we use in CARA most often. And it does make a lot of assumptions that we'll walk through, and we'll talk about where those might break down. The 3D PC was an attempt to eliminate some of the assumptions for the 2D PC method. Do assumptions, take a little bit longer to make the calculation, hopefully get a more accurate answer. But we'll talk about some of the drawbacks that came up with doing that. And then Monte Carlo is a brute force method that we can do that eliminates almost all, if not all, of the assumptions but it's going to take a lot longer because of that. But we'll walk through how you would do a Monte Carlo as well. All right, so 2D PC method. Like I said, it's the most common that we're doing in CARA. It's not very computationally expensive, so you can do lots of calculations in a short period of time, but it does require a lot of assumptions. So 2D PC calculation is only valid for conjunctions that are hyperkinetic, so your duration is really short. We have two objects flying by each other quickly, and therefore the motion is rectilinear, so you don't have to worry about the actual curvature of the orbits. You're going to assume that they're flying straight paths. The combined covariance for the two objects doesn't change during the encounter and can be held static. And then also, these error volumes that create the combined covariance are uncorrelated. And we'll walk through these in more detail. Because of these assumptions, though, 2D PC is going to underrepresent our risk. Most likely, when we have low velocity encounters, this comes up often. That's one of the prime uses of Monte Carlo is to evaluate low relative velocity events. Essentially, in those cases, your conjunction is not hyperkinetic. You have two objects encountering each other over a long period of time. Non-rectilinear motions, so generally occurring for the same reason as low relative velocity. Also, though, for some high velocity events where you have very long, thin covariances, this could cause an issue with the 2D PC because small changes to the orientation of the covariance could affect the PC a lot, but we're assuming the covariance is being held static. And there may be other edge cases as well for the 2D PC. So here's a little diagram that kind of shows some of these assumptions compared to reality. So the green is what we're assuming for 2D PC here. We have a straight line trajectory with our covariance being held static across all three points in time here. In reality, we have a curvilinear situation where the covariance matrices are changing both in shape and orientation. All right. So we have our assumptions. Our event meets these at a high level. How do we calculate 2D PC? So first we have to combine our covariances, and that's where the covariances being uncorrelated comes into play. That's crucial to be able to combine them into a similar reference frame. You also have to combine the two objects' hard body radius, define a conjunction plane, project that relative state and combine uncertainty into this conjunction plane. And then we're going to determine the portion of the position uncertainty that falls within the combined hard body radius area. So that's going to be what is the incursion into the hard body radius. And that'll be an integral in which we'll get the PC. So now we're going to walk through all this in more detail. So first, combining your error volumes. This is not too difficult. There's a proof in a paper by Chan in 2008 that shows that we can actually just add two covariances, presuming the states are uncorrelated. And by adding these two matrices, now we have the combined event covariance. So we started with our uncertainties for our primary, our uncertainties for our secondary. Now we have what the uncertainties are for the event. And then we transform that into a common reference frame that we're going to use to do our calculation. And this allows us to position all of the error onto one of the two objects, and we'll see how that comes into play later. So here's a little diagram of what that might look like. You're starting with two covariance ellipsoids about your objects, and then you're going to combine them and place them onto one of the objects. And we'll see that out here where the primary was. That's where we're going to place our hard body radius at the other end of our missed distance vector. So let's talk about hard body radius, just showing why we can add the two together for the primary and secondary. Essentially, we're using a circumscribing sphere about the two objects, and you can probably see immediately this could actually over-represent our PC in the end because we do have some open space in the sphere. But nonetheless, what we can do for the combined situation is simply put a bigger sphere around both objects, and that becomes our combined hard body radius. So it is somewhat conservative. Like I said, you have this empty space now. And there are other ways that we could go about doing this that become more computationally expensive, but that may come in the future with more advancements. But this is one reason that we've encouraged missions to have realistically sized hard body radius as possible so that you're minimizing the amount of conservatism from the calculation. All right, so now we're going to take the problem from our 3D down to the 2D, as we want to calculate a 2D PC. And we can do that because we've made the assumption that we have a rectilinear path and a quick encounter time. So in this little diagram, we have our soda straw representation of the trajectory for our primary object, going through the combined covariance about the secondary. And because it's a straight line trajectory that can be considered infinitely straight and long, when we integrate about that axis, it approaches unity. And so when we do our final integral in the third dimension, we're going to multiply by 1, and that allows us to eliminate the third dimension in our problem. So having the assumption that we have a straight line trajectory, a short encounter time is crucial for this. So in this diagram here, you can imagine actually taking a slice, projecting this image into the 2D, what we call the 2D conjunction plane now. So your combined covariance here is projected into the plane normal to the relative velocity vector. So going into the page here is your velocity direction for the conjunction event. And then you have your hard body radius here centered about the primary, and that falls on the x-axis at the missed distance is where the hard body radius is centered. So then we can look at what does the 2D conjunction plane look like in operations. This is the plot that we produce in CARA. So again, you have along the x-axis your missed distance direction. You have your hard body radius here centered about the primary at the miss. And then you have your covariance ellipses that have been projected into this 2D plane. And here we've identified the 1, square root 2, and 3 sigma ellipses for the combined covariance. And so when we do our PC calculation, we want to know how much of this covariance ellipse is going to fall within our hard body radius. That's the integral that we're going to do. It's going to be about the hard body radius. And one thing to keep in mind is even though we've plotted just the 1, square root 2, and 3 sigma ellipses, the uncertainty continues infinitely. It gets less and less percent of likelihood that you're actually going to fall into those larger sigmas. But just because there's this 3 sigmas here doesn't mean this is a 0 PC. In fact, this is something that's 3.6 10 to the minus 5. So you're just outside the 3 sigma ellipse in this case. And that PC calculation just depends on a lot of things. So here's the actual integral. Not going to get into it too much. But you are integrating. Here's the limits that have to do with the hard body radius. So that's why part of why the hard body radius is so important. That's what you're integrating about. And so when we actually go about to integrate this in operations, we're going to do that numerically. And there's a number of methods that you can use. We have a few here, the Foster method, Chan, Patera, and Alfano. So different smart guys coming up with methods to integrate this. We use the Foster method up top. It is the slowest of the ones presented here, but it's still does a calculation, I think in milliseconds. It's very quick. And so I think they get quicker as they go down, but there's just different ways that you can do it. Thankfully, the computer does it for us. Okay, so that was kind of walking through how we calculate 2D PC. I kind of already hinted at it, but there are times when the 2D PC equation is not going to be adequate for what we want. It's not going to provide us with an accurate PC. And when that happens, we are still researching that question. We know a few things. When the 2D PC is going to fail when you have an extended period of time between the two objects, so you're not having a quick encounter time, your motion is not rectilinear. We see these sometimes in like intra-constellation, like with MMS, because you have these two objects flying nearby for long periods of time. Also, Astro H, unfortunately, when it failed and had some pieces that broke off of the spacecraft, they were then orbiting just slightly next to the spacecraft, and calculating a PC between the spacecraft and those debris objects is not really possible with the 2D PC method. But what is an extended period? What is low relative velocity? What are those limits? That is still not totally defined. So we use a threshold of relative velocity less than 500 meters per second being low relative velocity, but this is pretty conservative. And it may be something closer to 10 meters per second perhaps, but studies that were done on that did not use real data. It was using synthetic data, so it probably needs to be revisited. And then similarly, if you have low relative velocity, you probably have an extended encounter time. Those are related, and so kind of the opposite also, what is a long encounter time? So we know those are where this is going to break down, but we're still researching to find where that turning point is. Okay, so now I'm going to briefly talk about 3D PC. I'm not going to get into it too much because we're not using it operationally at this time. It does get calculated, but we're really making our decisions based on the 2D PC or Monte Carlo. But I do want to talk about it a little bit. So the idea of the 3D PC is to not have to do the projection of the 2D plane. We are going to consider multiple dimensions of the events. To begin, we're going to set up the problem the same way. We're still going to do our combined covariance and our combined hard-body radius. So we're going to start the same way. But rather than picking a single instant in time, such as our time of closest approach, we're actually going to evaluate how the PC is evolving over time and how it might be changing. And so then we get a instantaneous rate of PC change, or the PC rate, which when you integrate that, you can come up with your PC value. And when we were implementing this, the hope was that it would provide us a more accurate PC when our 2D PC failed. And some of the other things that were nice about this, we could eliminate the rectilinear assumption. We could eliminate our static covariance assumption from the 2D PC. We would consider the velocity uncertainties. For 2D PC, we are only considering the position uncertainties for the two objects since we're holding things static in time. But for the 3D PC, we would have the ability to use both the position and velocity uncertainties. And so this is what it would look like, 4 instances of time, and you can see where the portion of the covariance that's incurred into the hard body radius changes, the orientation and shape and size is changing over time. So, that'd be good. 3D PC could capture that for us. And here would be the integrals to use to calculate it. Coppola worked this out in 2012, and then it was expanded further in 2014. And so here's what this would look like, your PC rate over time. So there's a peak PC, and what's interesting about the peak PC is this is actually occurring not at the TCA. TC is at 0 here. And that was something that was interesting that did come out of doing work on the 3D PC, is that your point of highest risk is not necessarily at TCA. And that's kind of interesting because you maybe think that you're at your riskiest when you're at your closest. But the reason this may not be the case is because of the way the covariance ellipsoid could actually change orientation, such that it may actually have more incursion when you're just off of TCA. You're still close to this object, but you're not the closest, but your covariance orientation is different. And so you actually have offset of your peak PC. And that's kind of interesting. So you take your PC rate over time, and then when you integrate that, what happens is it's going to approach some value. In this case, we picked an event that the 2D PC assumptions were valid, and that's shown in the magenta line. And so in this case, when we do our integration of all the time steps for the PC, we end up in this case getting the same result. So in this case, we were confirmed that the 2D PC calculation that we did was valid, which we would expect in this case because it met all of the 2D PC assumptions. And then I'm going to skip to this slide here. This is showing an event where, kind of interesting, something that is not going to be have a PC calculated accurately by 2D PC, because we actually have two discrete peaks in your PC that are occurring over about 2 seconds of time. And so even the 3D PC is kind of struggling, depending on how many. There's different modes that we could use it, and they use better force modeling. But in this case, we can see that as we get these up here are using more force modeling, and they're showing a very different PC value than the 2D PC in magenta. So this was a case where we were hoping the 3D PC could really be useful for us, where 2D PC was not giving us an accurate value. And maybe you're picking up on my language here. I'm going to explain why we're not really using 3D PC and why it seems like it'd be do such a good job. But unfortunately, when we actually implemented this operationally, we found flaws in the implementation. First, it's using Cartesian coordinates. And we found that for the velocity covariance, doing that in the Cartesian coordinate system introduced representation problems and gave us incorrect values. Basically, the velocity covariance is really sensitive to the Cartesian coordinates. If we could do the calculation in equinoctial, which is what we eventually developed in our Monte Carlo, is to do these calculations using the equinoctial coordinate system, then we get actually more accurate results. But the velocity covariance that we get is in Cartesian. And so what we did to fix this is actually zero out the velocity covariance. But then that essentially means the 3D PC is very similar to the 2D PC. And so where the 2D PC assumptions are being met, our 3D PC is equivalent to that. But in cases where the 2D PC breaks down, we don't actually trust the value that the 3D PC is giving us. So that was unfortunate. We don't totally understand why this happens. It could be in part because the velocity covariance that's provided to us through the ASW solution is not well tuned, and so it's giving us covariance is very sensitive to any slight changes. So unfortunately, we ended up all but removing the 3D PC from our operational system. We are still calculating it, but it's in most cases giving us the same answer as the 2D PC is giving us anyway. So we're really not using it much. All right, so that's the 3D PC briefly. I've got 2 slides on positive definite covariance. Just want to touch on that, and we'll be talking about covariance in more detail in the next slide package. But I guess as a little primer, so we've talked about how we've got the uncertainty about our 2 objects, and so that's defined by a covariance matrix. And in theory, those matrices should always be positive definite because that produces a physically meaningful result. And so, unfortunately, sometimes we do get covariance matrices that are non-positive definite. This happens due to truncation or rounding errors or having the data in Cartesian coordinates rather than in the equinoctial coordinate system. And so, while you can still calculate a PC using a non-positive definite covariance, we are hesitant to do that because we're presented with a matrix that's not representing the physical reality of the situation. So what can we do about that? These don't come up too often, but we do get them in the different CDMs that we receive for events. And the problem is accentuated when we have the larger covariance matrices. So when we're just using a 3x3 matrix, it's usually not too bad. But when we are using a 6x6 matrix for the position and velocity, and we actually get up to an 8x8 matrix that we'll talk about, that includes uncertainty on the ballistic coefficient. So the larger the matrix, the more things that we're trying to incorporate into one matrix, the more likely they are to be non-positive definite. It can also be caused when we're interpolating the covariance. So because we're propagating out to TCA, that may be in between a time step of the actual propagation. So you could have, like I said, the truncation, and also this interpolation could be an issue to cause the non-positive definite. In CARA, the way we address this is actually we have some remediation techniques that sort of massage the covariance because it's really very subtle changes in the covariance matrix that can make it non-positive definite. And so you could perturb some of the values by epsilon, a very small number, and actually cause the matrix to be positive definite. So that's what we do behind the scenes in our software for CARA. Another way that you could resolve a non-positive definite covariance could be by getting an updated CDM with an updated OD state in the background because a new OD may resolve any of those small perturbation errors. Okay, so that was non-positive definite covariance real quick. And then we'll talk about the last PC method here. So Monte Carlo. Well, and of course, there's a couple different ways you can do the Monte Carlo. We'll talk about that. So before I kind of get into the Monte Carlo simulation that we would do to calculate probability of collision, I'm going to talk briefly about using Monte Carlo to propagate or to identify your state error estimation. So you have your covariance matrix. Again, that's characterizing the errors in your state. And if you perform random draws from this covariance error ellipsoid, then you can produce this family of states that should reasonably state where this object is. So if you have the covariance at the time of interest, like that we get on a CDM where we have our event propagated out to the time of closest approach, so we have our covariance at that time of interest, you could do draws from your covariance to get this set of different states that represent where these two objects are. And similarly, you could take your epoch covariance at your OD epoch before you've propagated to TCA. You could take your draws from your covariance of these different states there and propagate that to TCA as well. And so there's pros and cons to both that we'll get into. So the different Monte Carlo techniques that we use for PC, some are using this technique of taking your draws at TCA, and some take the draws at the OD epoch and propagate that to TCA. And one benefit to taking the draws at the OD epoch is you don't have to worry about your covariance that you propagated in the first way out to TCA. You don't have to worry about whether that was realistic, because you're actually just propagating all these. All you have to worry about is that the covariance at the OD epoch is actually representing the errors there. But you don't have to worry about whether that covariance is propagated correctly. So we'll talk about that more. Okay, so plain language, how do we do the Monte Carlo PC calculation? We're going to perform random draws on the primary and secondary covariances, whether it's at epoch or at TCA, could be either. And then we get this family of states for the primary and secondary object. We're going to take pairs of states and propagate them forward to a time of closest approach. And at that time of closest approach, if the missed distance calculated between the two objects is less than the hard body radius, then it's a hit, and we're going to consider that a collision for this calculation. So you do that maybe 1,000,000 times, and you take the number of hits that you got divided by the number of trials that you ran, and that becomes your PC. So this is a brute force way, not to be confused with brute force Monte Carlo, which is another term we've used, but it's a brute force way to calculate PC. It eliminates assumptions about whether it's hyperkinetic or what the covariance might be doing, all of that, and just simply performs a lot of trials to get at your answer. And so we kind of have two flavors that go back to the previous slide, where we have this brute force Monte Carlo, where we're taking our states from the OD epoch and propagating that forward. And then we have our Monte Carlo from TCA, or CDM mode Monte Carlo, where we would actually take our draws from the covariance at TCA to do that calculation. And we'll talk about pros and cons of the two. Before we get into that, come back again to the Cartesian versus element representations, because this actually matters a lot for Monte Carlo, that unfortunately we found out the hard way. So going kind of background here, we need for three-dimensional states, we need 6 parameters to fully specify, 7 if you include time. And so in Cartesian, that gives us our 3D position and 3D velocity. And this is straightforward to visualize. Some force model applications actually do propagation with different force modeling, actually need the information to be in Cartesian, so that's kind of important. However, as I kind of had mentioned before, an element representation such as the equinoctial element set does a lot better at actually describing an orbit in terms of it being curvilinear, versus Cartesian is describing it in a rectilinear way. So what we found is that representation of the curvilinear nature of the orbit is actually very important when you do Monte Carlo. And if you don't realize that, and as we did do this in Cartesian, you could end up with inaccurate results. And so that's kind of what happened with the 3D PC. It was verified against our Monte Carlo, but both were using Cartesian to represent the elements, and so they both failed in the same way, and they agreed very nicely, so it seemed right. And it wasn't until later, and when we were able to develop the Monte Carlo that we have now that uses equinoctial, that we were able to show that you really do need to use the equinoctial elements. So yeah, different results obtained depending whether your sampling is performed in Cartesian or equinoctial. So here's a little diagram of that. So what's interesting, so for these first two, we're imagining a Monte Carlo from using the CDM, so at TCA. So as it turns out, when you're doing all this propagation here, that actually doesn't matter whether you're in Cartesian or equinoctial. What matters is when you propagate to TCA and you actually pull your samples. In this top example, notionally, that's Cartesian, and down here is what you might get for the same event, but if you did your polls in equinoctial. And so here we're seeing more representation of some of the curvilinear nature. We have different velocity vectors. This is a picture, but the point is you are getting different states when you pull an equinoctial. And so that's important. That affects the final PC that you're going to get from this tool. And then down here, this is showing the example of generating the samples at epoch and then propagating that forward to TCA. And so that could get you even another set of states to use, but they should be a lot more consistent with what you pull in equinoctial at TCA than they would be between that and pulling in Cartesian. So I'm not going to go through everything on the slide, it's a lot, but this is trying to describe different versions of Monte Carlo that we've developed in CARA over time. And so these, the threes here are pulling the states at TCA, and then down here is our brute force where we are pulling our states from the OD epoch. And really, the main difference is going to come down to the amount of time it takes to run. So if you think about pulling a million states at your OD epoch and then propagating that out, say 4 or 5 days, that's a lot of propagation, a lot of force models that you have to calculate. What is the atmosphere doing? Versus if you can take that same data at TCA and do the draws there and not have to do that propagation, it's going to be a lot faster. So the brute force Monte Carlo from the OD epoch is our gold standard. It's going to be the most accurate because you're doing this propagation. You're not worrying about your covariance realism when you're doing that. But there may be cases where it's really not feasible to run it in operations, particularly if you're trying to verify an event with a low PC. You could be looking at days of runtime to confirm that answer. So for some cases, we may really have to use the Monte Carlo with the CDM at TCA. And that's okay because we've seen that that is reasonably accurate for most events. Okay, so just a little bit more on Monte Carlo. How do you know when you've converged on an answer? It's kind of a final point here. So you've done a bunch of trials. How do you know the accuracy of that value you got? And so what you do is you actually get confidence intervals for your PC. And the confidence interval tells you, if it's a 95% confidence interval, it would tell you that 95% of the time, if you did this Monte Carlo trial again, you would get an answer within the confidence interval. So to improve your confidence interval, you do more trials, become more confident of what that value is. So we can calculate the confidence intervals, but pointing out on this slide and the next one is that it's important that we don't reuse our samples or the states that we pulled from our covariance, which we may be tempted to do because it can be computationally expensive to do all these pulls, and particularly if we're doing our brute force Monte Carlo to do those pulls and propagate that forward. So maybe we can try and get clever and reuse some of those states that we've pulled. But Russell Carpenter in 2016 published a paper showing that If you try to do something clever, say this multiple comparison method where you're comparing your primary state 1 to secondary state 1, secondary 2, and on, that actually invalidates the confidence interval calculation. And there may be other ways to calculate the confidence interval in this case, but it can't be done in sort of the typical way that you would do for a Monte Carlo. And it is possible that it would converge on a correct answer, but the point is the confidence intervals aren't accurate, and so you don't know for sure. So for now, we're kind of stuck pulling all these separate trials and doing that propagation. So here's output from our Monte Carlo, what that looks like. So on the left here, I ran this with 3.6 times 10 to the 4 trials, and this orange band here is the confidence interval, so it's quite large in this case. Again, the magenta is the 2D PC, and this dark orange is the Monte Carlo nominal PC. So you can see nominally it's a little higher than the 2D PC, but you have a pretty big confidence interval. Now on the right, I did 1.01 times 10 to the 6 trials. So a lot more trials, and the confidence interval has shrunk down quite a bit. We're still seeing a little bit higher nominal PC than the 2D calculated, but we might run this in operations and then could verify the 2D PC result that we got was accurate for this case. So that's what I had about probability of collision. So we should have time for some questions. If anyone has any. Yes?
So we put bounds on sort of the slow conjunctions when 2D falls down. Are there sort of bounds on the long and thin covariance?
Right, so the question asking whether there's bounds on how long and thin a covariance could be, I don't think that's well defined right now, but certainly an area of study.